This is Linear Regression Part 3, Homoscedasticity. There's only 2 slides in this part of the presentation, but we're going to spend a fair amount of time on each one. I have a new microphone, so hopefully it doesn't sound like I'm underwater like it does in some of my other videos. This plot is the first plot that you will often run when you're checking your linear regression assumptions. It can tell you a lot. This is the residual versus fitted plot. On the x-axis, you have the fitted value, which is just another way of saying this is the value that the model estimated the discharge mobility score would be. The residual is the difference between the actual score and the predicted score. So if you look at that data point at the top left, that is an individual in the data set for whom the model predicted a discharge mobility score of a little bit over 20, and the actual score was about 30 points higher. What you're looking for, this is the best way probably to check for the assumption of homoscedasticity. So what is that assumption? This means that the error variance is what you're looking at, is the spread of the dots above and below the line, would be similar throughout the range of fitted or predictive values. So what that would look like on a plot would be this plot with the dots evenly scattered above and below the line. For individuals that you're predicting a discharge score of 40, you'd expect a similar spread as you would see at 80 or even higher. Now, do we see that here? We do not. There are 2 problems, actually, that jump out at you just by looking at this plot. The first is the homoscedasticity assumption, which, at least by visual inspection, has been violated. And when that happens, you can see kind of a funnel shape is one way that it manifests itself. If you look at the fitted values closer to 80, between 70, 80, and going up towards 90, there's very little variance in the residuals compared to the lower fitted values, like around 40, where there's much more. So what does this mean in practice? What it means is that, remember, our model is supposed to predict discharge mobility scores. And our estimates of prediction are more precise as the predicted discharge mobility scores get higher. A lot of times you might not know what this is from, but in this case, we can make a guess. One of the issues with some of the instruments that we use in rehabilitation is that patients either do not have time, or they refuse, or they're incapable of doing a specific task safely. So when you have this ordinal rating scale, like the section GG coding system, where 1 is they can't do it and 7 or whatever the highest number is means they're independent, when you have something like that, oftentimes if a therapist doesn't feel comfortable evaluating a patient going up the stairs, let's say, they may mark it as not observed. And if you're actually scoring using the system, you're not supposed to count that towards the total. But for research purposes, that's a problem. So what we do is what we used to do with the FIM is in research studies, you kind of assign a value of 1 to the participant. Now, you haven't observed an activity, but you're giving a participant the lowest possible score on that activity. That's a problem, because it could be that their score was a 2 or a 3, and you don't know. You didn't see it. Okay, so this is a case where having more error variance in the lower ranges of predicted mobility scores at discharge makes a lot of sense. And it's a function of the measurement properties of the tool that we're using. That's not always the case. You may not know why it happens. And Violations of the assumption of homoscedasticity could occur in, you could see the funnel shape going the opposite direction, where as scores go up, the error variance increases. So we think we have a problem with the homoscedasticity assumption, and we may have to look at addressing it with several fixes that are actually fairly easy to implement. There is another problem on this chart, and see if you can figure out what it looks like to you. In addition to the non-constant error variance, you'll see kind of a line if you look towards the right side of the chart, starting above the red line and then going below the red line, you'll see kind of a slanted cutoff of the scores. And I see this with a lot of the data sets that I work with. What is it? Well, our instrument has a maximum score. And so participants are always going to run up against that if they have relatively high levels of function. However, when the model gets someone who has really excellent scores coming in, they're going to predict a discharge mobility score that is higher than what the instrument allows. And so if you look on the right side of this chart, you'll see a bunch of scores that were supposed to be higher, but the actual score was lower because it was cut off. So that's a ceiling effect. And that's what this looks like in this plot. And it's very, very common to see with instruments that have a ceiling. And I come across this a lot in rehabilitation research. This is a separate problem from homoscedasticity, and it is not easily solvable. So we're going to live with this one and accept it as a limitation. But heteroscedasticity is something that we can do something about. We've looked before we've tested, and we think we have a problem. In state and are there tests available to determine if homoscedasticity assumption has been violated? Here's one of them. And you could see here from the p-value, which is the very lowest line, that I wouldn't say very significant because there's no such thing, but this is clearly a significant test result, which rejects the null hypothesis that the variance is constant. And we can assume this confirms we have a problem with heteroscedasticity. Using statistical testing, I always think of it like clinical terms. You do your physical exam to see if a patient has a problem, and then you use a diagnostic technology to see if what you observed clinically is confirmed or not, right? And so you don't want to overuse testing. You always want to start by looking at the results first. Sometimes the test and the results don't exactly match up. Here, they clearly do. So we have a violation. Let's look at what we can do about it. There are a variety of standard error calculations that we can use to calculate both the p-values and the confidence interval of the coefficient, which is that estimate, first column, that account for violations of homoscedasticity. So if you look at the top, this is the ordinary least squares model that we ran initially. There's one different variance calculation, HC1, and in the bottom we have a slightly different calculation, HC3. There's other estimators out there. The R sandwich package has a lot of them. Stata has a wide variety of different calculations to choose from. You have to go into the literature to determine which one is best for you. Generally, I've read that HC3 is a little better with smaller samples than HC1. Now, we have a few hundred people here. I wouldn't call this small, but HC3 might be the way to go. Now, let's look. Remember, we said there's a problem with the variance around the estimate, but we don't have a problem with the coefficient estimates for the individual predictors. So if you look at the first column, the coefficients, the regression coefficients, are exactly the same no matter what variance calculation we use. What changes are the p-values and the confidence intervals. Sometimes the confidence intervals will shrink and the p-values will go down, but sometimes they'll get broader. If you use a different calculation, the p-values will go up. So if you look at the bottom, which is the one we're going to choose, cognition, the p-value goes down a bit from the regular model, and the confidence interval is now more narrow, but still not significant. This is a serious consideration, though, and I have worked with models where variables were not significant with the OLS calculation, the regular standard error calculation, but they were when I used one of these calculations. And also the reverse is true. Some were significant before, and then when you use a different calculation, they're no longer significant. That's really the case where you want to make sure you use the more conservative estimate. And if some of your key predictors are no longer significant when you use a different calculation, that's not an excuse to go back to the standard calculation. So of all these, I would go with the third. And you can see our model doesn't change that much, but it's worth it when we report to say we used heteroscedasticity consistent standard errors.